If you are new to the channel, then subscribe the channel and press the bell icon for further notification. So, welcome you all once again to lecture 24. If you see here what we are doing now we are doing your tau is not a special case. Tau is now between 0 to 90. Tau can take any value. So if you take any value of tau, now what will be your equation? This equation is something like that. So what I have told you, z set can be anywhere. So you think of some situation like that. Let me draw it in a blank space so that you understand this one. Suppose this is your r and this is your x. Now as I told you, your z set can be anywhere. Suppose let me draw this is nothing to do trip characteristics of ZIR, generic impedance relay. Just to understand, z set can be anywhere. So this is the line through in this line only. This is the line where you are measuring your ZR or ZL, whatever. Relay is sensing this impedance, and this angle is theta. Now if I take my z set here up to this much, this is my z set. The angle of z set is tau. Now what is theta minus tau is this angle. So you can now think what is theta minus tau, this one. So what relay will sense? Relay will sense whatever ZR you gave, suppose you give ZR this one, it will take cos component of that one. What is cos? Cos theta minus tau, so it will come here. This is 90 degree. Or should I draw it again? This time no circle I am giving. So this is your ZR, suppose I am not writing ZL, relay is sensing this. This is theta angle, and suppose this is my z set value, and I have given the angle of taken angle of that one is tau, because z set can be anywhere, it can rotate in circle anywhere. So now suppose I am taking ZR here, so this is my theta minus tau. So what will be cos component? This is. So if this value is less than your z set is here, then it will trip. So now we are getting, so if whatever ZR, it will take cos minus theta, it will come here and it will search in this axis what is z set in this axis. In this line, what is the value of z set? If it is less than, it is falling less than that, then it will trip. So ultimately it will look around a perpendicular line, this perpendicular line to your z set. If anything falls below that, it will trip. So this zone becomes trip. So that you will see in the drawing here itself. So this was your z set. Anything a perpendicular, this is your z set. So if you are calculating ZR, suppose here I have taken a consider, then you take cos component is like this, so it is less than this, that's why it will trip. So anything comes less than this line here, so this becomes your trip zone, and that side becomes your resistance zone. So this is generic impedance relay. So by changing the tau is in our hand. You can change it tau. You can remember tau was 90 minus theta PC, which is done from the directional unit. That theta PC you can change by changing capacitance and resistance. You can go back to the video and you can check how you are changing the tau. So this is known as, so this is also special purpose use. You can use a specific line if you want to draw, so that your trip should not go beyond that. So in that case you can use this generic impedance relay with specific tau. That is also some use, but we will not go that far. We will leave it up to resistance and reactance relay. So resistance and reactance relays are specific GIRs generally used in distance protection. Now you can see no GIR exhibits directional features. No GIR exhibits directional features. This one. Why? Because if you see in the characteristics, all the characteristics, this one, all the four quadrants. If you see the characteristics of resistance relay, this was the trip characteristics. So all first quadrant, second, third, fourth, all are here. So for directional we need only first quadrant. If the trip characteristics occupies only in first quadrant, then we say it will trip only in forward direction. So that then it will be a directional property. It will trip only in one direction. But you can see it as it is occupying third quadrant also. So you have seen third quadrant is for reverse operation. So obviously it is not a directional resistance. Similarly, you can think of reactance also. Reactance, your trip characteristics is this. anything falls below. So again first, second, third, fourth, all four quadrant falls below that, everywhere it will trip. So again this is not also a directional property. So no GIR will exhibit a directional property as it will contain all the four quadrants. Now one interesting thing, I am not going here, I am directly written here. For interconnected system or doubly fitted line, we have discussed this one. This is forward, this is normal, this is reverse. You can think, check earlier videos, but that was for fault condition, when you are measuring only thinking that there is a fault in the transmission line, or you can think on a single feeding radial line, source is coming from only one side. But in power system it is always interconnected, there is always a double side feeding, power can come from this side, power can come from that side also. So generators are connected in all where. So in an interconnected system, the simplest one is the doubly fitted line. If you draw the normal operating point, you will find it is coming in third quadrant somewhere here. So I have just drawn it here for your reference. This is the line, it is coming something at an angle of 90 degree to this. How it came here, I will not go there because it will take again some time. What I will do, I will put an extra lecture on this one to show that the normal operating point is in the third quadrant. For now you just remember that it is in the third quadrant, because if I go this one, that will go again so far. But I will put an extra lecture. So if you have leisure time, if you have extra time, if you want to know little bit extra why your operating point is going in, or how it is assumed that it is going to be in third quadrant, so you can think, you can have a look that one. So we'll put an extra lecture on that one without any numbering. Extra lecture I will write it. So you can see now, so the reactance relay will mal-operate during normal power put, because what was the characteristics of reactance relay? This is something characteristics of reactance relay. Your normal operating point is falling in the trip zone of, it is in the trip zone of reactance relay. So if you put a simple reactance relay, it will always trip. Your normal operation, it will always trip. So that's why reactance relay never used alone, it is always used as a supportive role to other relays, in mixture with other relays. Now, but resistance relay will not mal-operate, because resistance relay, you can see the resistance relay. What was the characteristics of resistance relay? Resistance relay characteristics was something like this. Here it will trip, but the S1 you can see it is in the restraint zone. So resistance relay it will not trip. Okay, normal operation it will not trip. Now one more thing, if the arc faults, that is arc resistance or insulation flashover that we have discussed in SIR case also, it is highly resistive. So if it is a resistive, then if you see the reactance curve, this one, and this was your Z set. So if it is resistance, if you add resistance with your ZL if you add R, which side your ZL will move? It will move this side only. Suppose you have fixed your Z set here. So if you add R, it will move this side only. So it will move this side only. Anywhere it will move, but X will always remain same. The reactance part will always remain same, because you are adding only R. Resistance you are adding, so it is moving in this direction only, but this magnitude also remains same. So every time it will be under trip characteristics only. So if you, in that faults, the resistance faults, the faults which are resistive in nature, that doesn't affect the reactance relay. So reactance relay will trip it, that will not get any affected. There will be no problem of underreach and overreach. But it will make the resistance relay underreach. Why? Because in resistance relay, the characteristics is this. Your Z set is this. So if you add R, it will move here. So it will go beyond your trip zone. So the entire line will not be protected, because you are adding ZL plus R. So it will move far for the entire line. Suppose this was your line length, so this was your ZL. So if you add now Z, suppose there is a fault, if you add ZF, so this plus this will give you this much. So if you fault anywhere here, it will go beyond that trip zone. If you add here, this ZL plus ZF will extend that boundary, because you are adding extra resistance, so it will move here. So the end point of the line will come here, because the end point it will get full ZL plus ZR. So if there is a fault in end point, it will reach here. It will not reach in the trip zone. So the relay will not operate for the full line. So it will underreach. Underreach means it will not going that much. That was suppose it was reach was 100 km. Now it will trip only up to 80 kilometer. Beyond 80 kilometer it will not trip. What happened beyond 80 kilometer? For that 20 kilometer resistance we have put in as a fault resistance, so it has crossed this position. So anything beyond that 80 kilometer beyond, if there is a fault, it is going outside its trip zone. So your resistance relay becomes under reach. That's why the reactance relay is popular, because it is not affected with your resistive relay. Because maximum of the fault, that is arc flashover, insulation arc, insulation flashover, these are highly resistive in nature. So that's why reactance relay, because there is no problem of reach, the reach remains same, that's why it is highly popular. But if your fault is a reactive impedance, fault is reactance type, suppose the fault impedance is not R, now it is highly reactive, now the reverse will happen. Now the resistance relay will not make any difference, but because you are adding now X, with ZL you are adding ZF as a X, your ZF is X. So if you are adding X, it is moving up. So resistance relay will remain same, but your reactance relay, because you are moving up, so it will go outside that trip zone. So it will be reverse case. Down reactance relay will be under reach and resistance relay will be remain same. So you have to think what fault impedance. If you are adding R, then reactance will not be affected. Only R will be affected. If you are adding X, then R will not get affected. Only reactance will be affected. As simple as it is. Okay, that's all for generic impedance relay. If you like the video, then press the like button and please give your valuable comments in the comment section.